We present OpenFrontier, general navigation with visual language grounded frontiers. Recent navigation methods achieve strong performance by fine-tuning VLMs. They leverage powerful image reasoning, but require large-scale in-domain data. Conventional geometry-based methods extract navigation targets from maps. They are fast and interpretable, however, usually rely on handcrafted metrics. OpenFrontier combines explicit target finding and image-based VLM reasoning. It extracts, reasons over, and plans with sparse visual frontier representation. The core concept is what we call a visual frontier. Conventional methods build a map, extract frontiers as the boundary between known and unknown space, and let the robot move toward them. However, 3D map is not always necessary for this process. Similar frontiers are often recognizable directly from the RGB image, using rich contextual cues. Visual frontiers appear as sparse targets that point toward unexplored place or occluded region. Beyond detecting visual frontiers, we can also semantically reason about them. With the image context, a pre-trained VLM is good at estimating what kind of region each frontier may lead to. This gives us the key idea. We detect and evaluate visual frontiers directly in image space. For detection, we build on FrontierNet, our previous work for predicting visual frontiers directly from RGB images. FrontierNet is a learning-based method that predicts visual frontier regions and estimates their information gain, namely how much unseen 3D space in volume they may reveal. FrontierNet performs inference on RGB images, but learns from geometric supervision. Projected 3D frontier voxels supervise the 2D frontier regions, and nearby unexplored volume supervises the information gain score. We then take the clustered visual frontiers and overlay a marker for each frontier on the same RGB image. With these, we query the VLM using set-of-marks prompting. Given the image, the markers, and a language goal, the VLM scores how likely each frontier is to lead toward the target. This gives us an efficient way to evaluate task relevance, keep the same visual frontiers, change the language query, and let an off-the-shelf VLM reason over the candidates. Furthermore, with depth from sensors, monocular priors, or multi-view estimation, we lift them into 3D, and they naturally become planning targets. This also gives the robot a lightweight long-term memory of the scene. It can prioritize among all active frontiers for optimal global planning, while also update their weights, remove outdated frontiers, or add new ones during navigation. This simple design is highly effective. On ObjectNav task, OpenFrontier shows competitive performance against dense mapping baselines and fine-tuned models, without relying on either. It also stays stable across different off-the-shelf VLMs. It can handle more diverse and open-ended instructions as well. And we also deploy OpenFrontier on a real robot. Since the VLM reasons over keyframes and outputs 3D targets rather than reasoning actions at every step, the system can run asynchronously and achieve good real-time performance. To summarize, OpenFrontier uses visual frontiers to connect target grounding, VLM reasoning, and global planning. This gives us an effective and extensible navigation framework, which also generalizes well. Welcome to visit our website or read the full paper for more details. Thank you for watching.